Merci d'être de retour parmi nous. Nous allons commencer par la présentation de Yash. Dear students of Yash, welcome. You may now start your presentation on social distancing in the classroom.
Okay, so hello everyone, my name is Ilinka, and together with my classmates, Andrea, Colleen, and Magda, we are going to present you the solution of the problem with social distancing in the classroom. But before that, let me introduce you to our teacher, Ioana Cătălin Anton, from Costache Negruți National College of Iași, and our researcher, Iulian Stoleriu, from University Alexandru Ioan Cuza of Iași, Romania. So in this problem, we have a rectangular shape, and we had to find out the maximum number of people, students, plus a teacher who could fit in the classroom while keeping a social distancing. Now my classmate Andrea will explain the solution of the problem for you.
Okay, so in the first part of our problem, we are given a classroom of a rectangular shape 8 meters by 14 meters, and we have to decide what would be the maximum number of students plus a teacher who could fit in this classroom while keeping a social distance of 1.5 meters. Well, in order to solve the problem, we considered different methods of placing the people in the classroom. For this, we filled the rectangular surface with 1.5 meter side squares, equilateral triangles with a side of 1.5 meters, regular hexagons of side 1.5 meters, or circles with a radius of 1.5 meters. We used an application called GeoGebra, and we got different distributions of the people in the classroom, and also represented the position of each person in the classroom with one colored dot. Finally, we decided which method gives us the best coverage and the biggest number of people. As you can see in the screen, we got 5 representation of the surface. I will start and describe each of it. The first one, the representation number 1, was made with squares of side 1.5 meters, and using this method, we can place 60 people in the classroom. Then the second one, with equilateral triangles with a side of 1.5 meters, allows us to place 67 people in the classroom. Then we move to the next one. Representation 3 is also made with equilateral triangles, but this time the triangles are placed a bit differently. We started putting the triangles on the width, not on the length, as we did in the previous representation. So using this method of arrangement, we get the number of 61 people who could be placed in this classroom. The next one was made with circles of a radius 1.5 meters, and using it, we can arrange 44 people in our classroom. And the last one was made with regular hexagons of side, again, 1.5 meters, and we get a number of 67 people. If we look at the representation that we made, we see that the most favorable methods of placing the people in the classroom are the ones with equilateral triangles, as you can see on the screen, representation number 2, or with regular hexagons, representation number 5, because we get the same number of people. And as I mentioned before, we get a number of 67 people, meaning 66 students and 1 teacher, who could be placed in the classroom while respecting the social distance of 1.5 meters. Now we get to the second part. In the second part, we had to decide how does the number of students change if the social distancing becomes 2 meters. And as in the previous case, we have, again, different ways of arranging the people in the classroom. But what's different is that this time we change the dimensions of the geometric figures. So we fill the rectangular surface with 2 meter side squares, equilateral triangles of a side 2 meters, regular hexagons with a side equal to 2 meters, or some circles with a radius of 2 meters. These are the representation that we got using, again, the GeoGebra application. The first representation with squares of side 2 meters allows us to place 40 people in the classroom. Then the second one, which was made with equilateral triangles of side 2 meters, allows us to place 38. Then moving forward to the next one, the next one is again with equilateral triangles, but as I mentioned in the first part, this representation is different than the other one with equilateral triangles because we place the triangles, we start placing them on the width, not on the length. So this is why we get a different number, meaning that we get a number of 41 people in this case. Then the fourth one is with circles of a radius 2 meters. As you can see, we get a number of 28 people, which is not a really favorable number of people because it's a much smaller number. So this method is not that efficient. And finally, the last one with regular hexagons, we can place 38 people while respecting the social distance of 2 meters. Considering the social distance given, 2 meter, we decided
Right. So my colleague probably said that using the equilateral triangles is the best option. And we assume that the width is small l. Oh, sorry, I should do this share screen. Wait. Here, I hope you can see. All right. So we assume that the width small l and the length big L are positive numbers and the width is smaller than the length. So from those previous figures, we observed that there are two cases.
Sorry, Magda, we cannot see anything.
No?
Maybe you can share one more time, please.
I don't know why, but here again. Can you see?
Yes, wait a second.
Sorry.
I can see. For me, it's okay. We can see.
All right.
You can continue.
We assume that the width small l and the length big L are positive numbers and the width is smaller than the length. So from those previous figures, we observe that there are two cases. We can discretize the length big L, but also we can discretize the width small l. Firstly, we consider two particular unnatural cases, values for the social distance d. 1.5 meters and the other one should be 2 meters. So for case 1, for the first value of the social distance, 1.5 meters, we consider an equilateral triangle's coverage with a side equal 1.5 to 1.5 meters. Of course, the height of such triangle can be calculated. Then we notice that the number of distances on the one length of the rectangular shape is the integral part of big L over 1.5. We also observe that on the odd numbered columns, we can put integral part of big L over 1.5 plus 1 people, while on the even numbered columns, we can place a number of people equal to integral part of big L over 1.5 people. As you can see on the screen, we have denoted K1, the number of columns, and by N1, the maximum number of people which can be seated on the rectangular classroom with the size small l and big L. Depending on the parity of K1, we get two different formulas for the maximum number of people and 1. But these two formulas can be rewritten in a single one. That is, N1 is K1 multiplied by integral part of big L over 1.5 plus integral part of K1 plus 1 over 2. For the social distance d equal to 2 meters, we obtain that the same formulas, where 1.5 is replaced by 2, we generalize this formula for the social distance d. Wait, can you see? We generalize this formula for the social distance d, a positive number. We get that the maximum number of people is equal to k1 multiplied by integral part of big L over d plus integral part of k1 plus 1 over 2. In the second case, we discretize the width. Small l and covered the classroom with a triangle grid. The number of distances on one width of the rectangular shape is the integral part of small l over d, denoting with k2. The number of columns, we get the maximum number of people on N2 equal to K2 multiplied by integral part of small l over d plus integral part of K2 plus 1 over 2. In conclusion, based on the previous calculation, the optimal number of people sitting in a big L times small l rectangular classroom is the maximum value of N1 and N2 previously obtained. Now my classmate Colleen will continue.
We demote by d, the length of the social distance, capital B, the larger base of the trapezoid, lowercase b, the smaller base of the trapezoid, h, the height of the trapezoid, and the height of the equilateral triangle. Capital B equals 7 times the length of the social distance. Lowercase b equals 3 times the length of the social distance. The height is the length of the social distance times square root of 3 divided by 2. The height of the trapezoid is equal to 4 times the height of the equilateral triangle, which is 2 times the length of the social distance times the square root of 3. The area is 10 times the social distance square times the square root of 3 square meters. So the minimum requirements for the classroom that would accommodate everyone and maintain social distance d would be able to have the area equal to 10 times d square root of the 3 square meters.
I would like to add that when we first started solving the problem in this part, we thought that maybe we should add a teacher. So we got a number of 31 people, and we got different distributions of the people in the classroom. But finally we decided that maybe we should stay with a number of 30 after our researcher suggested this. But this was the thing I wanted to add.
Thank you for your attention, and we hope you like it.
Okay, thank you for the presentation. I think my students are ready with their proof. If there are any questions for the presentation, I think
Thank you, I'm muted.
Ah d'accord. Ben, donc tu peux dire, tu peux encourager les gens à poser des questions en français sur le chat.
Est-ce que je leur dis que c'est votre question? So for now, you don't have any questions. I'm just going to ask on the chat on YouTube if anyone has any, okay? So just 1 second. Donc, est-ce que quelqu'un a des questions pour cet exposé sur avec l'école de Yash? Non? Il n'y en a pas. Okay, so the next presentation is table arrangements. So off you go.
Hello. Good morning, ladies and gentlemen. My name is Matthew and my classmate is Sărcu Eliza Maria, and we will present you table arrangements. Our teacher is Ioana Catalina Anton, and the researcher is Iulian Stoleriu.
A few keywords of our presentations are trace, corners, radius, size, rectangle, length, and width.
Now we will introduce you the problem we had to solve. In the canteen of a certain high school, all eating tables are around and of various sizes. The serving trays are of rectangular shape, x times y, all of the same size. Students place their trays with food on the table such that two adjacent corners of each tray are on the edge of the table. The trays are not overlapping, and the students align them in the same way. How should they align their trays so that the table indeed is as small as possible? What must be the radius of the smallest table that can accommodate n non-overlapping trays if were moved the condition that two adjacent corners of each tray must sit on the edge of the table? What about trays of a square shape?
What did we do for the first time? Well, we considered the first case in which R is the radius of the table and the trays are placed lengthwise. Their arrangement can be seen in the following drawings that we made by using the GeoGebra app. We note by n the number of trays, which is a constant. The first time we saw the problem, we consider it as a typical problem, but we were only half right because we'll also use some trigonometry notions. Angle DOC equals to 2 pi over n, and also angle DOC equals to 2 angle MOC. From relations 1 and 2, we deduce that angle MOC equals to pi over n, and that means that alpha equals to pi over n. We used Pythagoras theorem and the cotangent formula in the right triangles MON and NOC, and we obtained the formula R squared equals to x squared over 4 plus x over 2 times cotangent of alpha plus y, everything squared. After we finished the first case, we tried the other one as well. In the second case, Q will be the radius of the table and the trays will be placed on the width. The arrangement can be seen in the following images. We used the same formulas and the same algorithm as in the first case, and we got the formula Q squared equals to y squared over 4 plus y over 2 times cotangent of alpha plus x, everything squared.
We compare the square of radius. This is the algorithm we used to arrive at the formula. R squared minus q squared equals 1/4 times x squared minus y squared times cotangent of alpha minus 3. We realize that x squared minus y squared and 1/4 are constants, relations from which we came to the conclusion that cotangent squared of alpha minus 3 is the only variable, which means that cotangent squared of alpha is the only variable. Since 2 alpha is less or equal to 360 degrees, that means alpha is less or equals to 180 degrees. We deduce that as long as alpha is a divisor of the number 180, an exact number of trays will fit on the table, which will have the value equals to 360 degrees over alpha. Cotangent squared of alpha equals 3. That means cotangent of alpha equals plus other minus radical of 3, from which we deduce that cotangent of alpha equals radical of 3, and that means alpha equals 30 degrees and n equals 6, which is a natural number. If cotangent alpha equals minus radical of 3, that means alpha equals 150 degrees, and that means n equals 6/5, that isn't a natural number. If n equals 6, that means alpha equals 30 degrees, that the angle of the center is 60 degrees. That means r squared equals q squared. So it doesn't matter how we arrange the trays because the size of the table remains the same in the above situations. If n is more than 6, that means 30 degrees is less than alpha and less than 180 degrees. That means cotangent of alpha is less than 3. That means q squared is more than r squared. And the last case, if n is less than 6, that means 30 degrees is more than alpha. That means cotangent of alpha is more than 3. That means q squared is less than r squared.
Therefore, we took some concrete examples, namely when the number of trays is equal to 4, 5, 8, respectively 9. Now you can notice that in the cases when n equals to 4 or 5, the table is slightly smaller when the trays are placed on the width. In the cases when n equals to 8 or 9, the table is slightly smaller when the trays are placed on the length. It can be observed that for any number of trays smaller than 6, the variant in which the tray is placed on the width is more efficient, and if it's larger than 6, the one in which the trays are placed on the length is more efficient. We noticed that what could be more fascinating than finding something interesting in a math problem without being asked to? Well, we discovered something like that. Moreover, these are some exceptions to the basic rule that we announced before. We noticed that if the length is longer than the table radius, but the width is much smaller than the radius, it will be more efficient to place the trays on the length, not on the width. And if the width is bigger than the radius of the table, on the table will only fit one tray.
Eliminating the condition that 2 adjacent corners of each tray sit on the edge of the table means having more space to arrange the trays. As above, the space left between the 2 trays and the one in the center can now be filled by them. We took some concrete examples and noticed that a favorable case would be the one whose length is twice the width, so x equals to y. Another favorable case would be the one in which the length is 3 times the width, so x equals 3 times y. Therefore, we realize that in order to have the smallest radius, it would be useful for the length to be a multiple of the width.
If the trays are square, x will be equal to y, so it doesn't matter how we place them. If the square trays respect the case of adjacency, we can calculate the radius of the table by processing the formula obtained in the case of rectangular trays.
Since in the case of square trays, the length is equals to the width, the formula becomes r squared equals x squared over 4 times cotangent squared of alpha plus 4 times cotangent of alpha plus 5.
If the trays are not placed with the adjacent corners, we will have more space to arrange them on the table, as it can be seen in the following drawings, in which we also inserted some real-life examples. Since it was a tender subject and we were passionate about it, we decided to do some tests if, instead of trays, we used plates. Thus, since the number of plates used is calculated by the formula n equals to pi times r squared over pi times q squared, where r represents the radius of the table, q the radius of the plate, and the number of plates, we could deduce the formula to find the table radius. R squared equals to n times q squared.
Our conclusion is that reduction of the size of the table, fewer trays will fit on the table. In order for the table to be as small as possible, and for the number of trays to be bigger than or equal to 6, they must be placed longitudinally. If the number of trays is less than or equal to 6, they must be placed wide. If the trays are square, their arrangements does not matter. However, now with this pandemic, we cannot place the trays to have adjunct corners because the distance of 2 meters between two people would not be respected.
This was our presentation. Thank you for watching it.
Donc, thank you very much for that really wonderful presentation. If you have any questions for the public, you can ask them now. Merci beaucoup pour cette présentation, c'était vraiment super. Si vous avez des questions, vous pouvez les poser dans le chat YouTube. On vous laisse 2 minutes. For the moment, there are no questions. So I think we can pass to the next presentation. The next presentation is on double. So off you go.
You are now muted.
Tu peux le présenter
en anglais.
Attends ton arrivée.
Je présente en anglais. Hello, welcome everybody. You can now start your presentation on double and off you go.
Good afternoon. Double is a game which have 55 cards, and on each card there are 8 different symbols. The cards are displayed on a surface with their face down. The game consists in turning 2 cards, and the first player who finds a pair of cards representing the same symbol wins. For this reason, every card in the deck is made so that in every pair of cards there is only one symbol in common. This doesn't mean that a symbol can't appear in more than one card. For example, you can see in the photo the glasses symbol appears more than once. The question that we were asked are these: if there are m symbols on every card, what is the biggest amount of cards that the card deck can have? What would the total amount of different symbols in the card deck be? And can you find a method to create a game like this? We started by making various theories. We began by those that are more specific, but that doesn't answer the question they asked us. We wrote the most interesting ones in the next slide. The first theory we made consists in infinite cards. By putting the same symbol in common on every card, we could create cards endlessly. Naturally, the game isn't playable and enjoyable, so we left this theory aside.
For this reason, we introduced some rules. 1. A symbol cannot appear on just one card. 2. A symbol cannot appear on all cards. For every m number of symbols per card, there is always a minimum number of possible cards, C, makeable, and a maximum on which contains all the possible combinations. All the other possible combinations are subset on of the maximum case. Let's study this case. To explain this, we made some notation. So C is number of card, M is number of symbol per card, and T is number of total symbol. We made an observation. We realized that if there are m symbols per card, then each symbol cannot appear more than m times. So we have demonstrated it. Let's suppose that there are n cards with the symbol x1, and that every card must contain m minus 1. Different symbol minus 1 because there is already x1. According to rule number 2, which we described in the slide number 6, there must be a card C that doesn't include x1, but because it must have something in common with all the other cards, it will contain a symbol from every other card. Thinking absurdly, if there was an extra card having the symbol x1, in order to be different from all the other cards, it should contain m minus 1, different symbol from the previous ones. so it wouldn't have anything in common with the card C.
Now we are going to demonstrate this graphically with the M, so the symbols being the 4. And to find the first combination of cards, we put a symbol x1 in every of the 4 cards. So going with the pattern of the rows, we had the cards x1, x2, x3, and x4, x1, x5, x6, and x7, x1, x8, x9, and x10, and x1, x11, x12, and x13. And to find the second combination of cards, we decided to represent in all the cards the symbol x2. But this time, for the pattern, we chose the one of the columns. So we obtained the cards x2, x5, x8, and x11, x2, x6, x9, and x12, and x2, x7, x10, and x13. To find the third combinations of cards, we put in all the 3 cards x3, and this time we used another pattern where we go diagonally rightwards. So we go down by 1 box, and then we go across to the right for another box. So we found these 3 cards that are composed from these symbols: x3, x7, x8, and x12, x3, x5, x9, and x13, and x3, x6, x10, and x11. And for the last combination, we put x4 in all the 3 cards, but this time we used a very similar pattern from before, but we don't go across for only 1 box, but we go for 2 boxes right. So we obtain the symbols, the cards, sorry, x4, x5, x10, and x12, x4, x6, x8, and x13, x4, x7, x9, and x11.
So we noted that x1 appears m times, so x1, the symbol x1 appears times, and x2, x3, and x4 appears m times, so the symbols appear 4 times. And we noted that it's applicable for all the symbols, so x5, x6, x7, x8, all the symbols from x1 to x14 appears m times. Sorry. But we made ourselves a question, and why did we always change the method to create combination? And we changed the method because the cards always need to have one symbol in common with the other ones. For example, if we hadn't changed the method to create a combination which have the symbol x3 or the combination which x4, we would have had more than only one symbol on a card in common with another card. How many cards did we get in total? We obtain m cards with x1, so 4 cards, 2, 3, and 4 cards which contain the symbol x1, m minus 1 cards with x2, because we don't count the card who contain x1, m minus 1 cards with x3, and m minus 1 cards with x4. And we get this formula, m squared minus m plus 1, so m squared 16, minus m equal 4, so minus 4, plus 1, 15 cards, or more simple, 4, 3, 3, 3, 4 plus 3 plus 3 plus 3, 13. And how many symbols did we obtain in total? We obtain 13 symbols from x1 to x14, and we get the same formula, so m squared minus m plus 1, 16 minus 4 plus 1, 13 symbols. And why this formula is the highest combination? is the highest combination because when we started writing all the symbols of the cards which contain x1, 4 cards, we can't add any other symbols. For example, if we added a card containing the symbols x14, this one would need to have in common only one symbol with all the other cards. It can be x1 because it's already appeared 4 times. So it needs to be one of the other symbol like x2, x5, x8. But by this way, it remains only one card, the last one, which didn't have any symbols in common with the card which contains the symbol x14. So, in conclusion, if there are n symbols on every card, what is the maximum number of cards the deck would have? With n symbol on every card, the maximum number of cards is n squared minus m plus 1. And what would the total number of different symbols be? The total number of different symbols is the same formula of the card, so m squared minus m plus 1. And could you provide a method to create like this? An example is the one written in this presentation. So for the one, use this method. For represent the other cards, use this, and all the method we use. This is the end of the presentation. Thank you for your attention.
Thank you very much and well done for your presentation from the School of Mestre. We will now pass to the students of Yash. They are doing a presentation on breeding like rabbits. And off you go.
Present our problem called breathing like rabbits. Hello, we are students in 11th grade at Kostaki Negru International College in Iași, and we are going to present our problem called breathing like rabbits. This year, our teacher is Adriana Zanoski, and our researcher is Ilias Tolerariu from the Faculty of Mathematics Alexandru Ioan Cuza of Iași. Now I shall introduce Ioana and let her begin the program.
Thank you, Sabrina. Hi, my name is Ioana, and these are some of the main points of our presentation. I shall start by presenting the research topic. In this paper, we approach the breeding like rabbits problem, which has always been a popular subject in the mathematics world. By doing so, we intended to study the evolution of a group of rabbits after a set period of time. To solve the problem, we started with an ideal case where the mortality rate is null. Then we considered a more realistic approach, including other variables. Here is a brief presentation of the conjectures and results obtained. We know that a certain species of rabbits may reach maturity after only 1 month of life, after which they can breed. However, not all the rabbits will reach maturity within 1 month. Let's suppose that for this species, the grow-up rate within 1 month is p, where p is between 0 and 1. We also assume that the birth rate for this species of rabbits is b, while d and capital D are death rates for immature and adult rabbits, respectively. In the first month, we start with M male-female rabbit pairs. We want to build a mathematical model for the dynamics of the rabbit population after n months. For some specific values of the above parameters, we want to draw a graph for the evolution of the number of rabbits within the next years and find the percentages of adults in this species after a large number of years. Now I shall let my colleague Medea continue.
Thank you, Ioana. We shall start with the solution. At first, we decided to start with an easier problem, which we later adjusted to ours. Fibonacci's rabbit is a problem that Fibonacci investigated. It was about how fast rabbits could breed in ideal circumstances. The problem included a newly born pair of rabbits, one male and one female, that are put on a field. The rabbits are able to mate at the age of 1 month, so that at the end of the second month, a female can produce another pair of rabbits, one male and one female. Let us assume that our rabbits never die and that the female always produces one new pair every month from the second month on. Knowing that, we can observe that at the end of the first month, they mate, but there is still only one pair. In the next month, the female produces a new pair, so there are 2 pairs of rabbits in the field. At the end of the third month, the original female produces a second pair, making 3 pairs in all in the field. In the fourth month, the original female has produced yet another new pair, and the female born 2 months ago produces her first pair, making 5 pairs in our field. If we let f of n mean the number of pairs of rabbits in the field at the start of the nth month, we will show that f of 1 is equal with 1, f of 2 is equal also with 1, and f of n is equal with f of n minus 1 plus f of n minus 2 for any n greater than 2, which is exactly the definition of the Fibonacci sequence. For all the rabbits from the previous month survive, so there are at least f of n minus 1 of them. Any rabbit that is alive 2 months ago is now able to produce a new pair, and we assume they will always and will each will produce only 1 new pair per month. Thus, the number of newly born pairs is the same as the number of pairs alive 2 months ago, which is f of n minus 2. Since all the rabbits were alive last month or are newly born this month, we will have f of n is equal to f of n minus 1 plus f of n minus 2 for n greater than 2, which is exactly what I wanted to demonstrate. We shall start with the Fibonacci sequence, which is xn plus 1 is equal with xn plus xn minus 1 for n greater or equal than 1, which is a second order recurrence. In order to find a solution for our Fibonacci sequence, we will start by solving the following equation. Alpha squared minus alpha minus 1 is equal with 0. The equation has the solution alpha 1 and alpha 2. And if we go back to our equation, we can observe that alpha 1 plus alpha 2 is equal with 1, and alpha 1 multiplied by alpha 2 is equal with minus 1. So our recurrence formula can be modified to what is now shown on the screen. We deduce that yn with n greater or equal than 1 with yn is equal with xn minus alpha 1 multiplied by xn minus 1 with n greater or equal than 1 is going to check the following equation. Yn plus 1 is equal with alpha 2 multiplied by yn with n greater or equal than 1, which is a geometric progression with ratio of alpha 2. So yn will be equal with alpha 2 at the power of n minus 1 with n greater or equal than 1. We will have the following equations, and when we add the equations above that have already been multiplied with the indicated numbers, we will obtain that xn is equal with alpha 2 at the power of n minus alpha 1 at the power of n divided by alpha 2 minus alpha 1. Thus, we can see that xn is equal with the formula shown on the screen. And if we annotate 5 with 1 plus square root of 5 divided by 2, we can rewrite xn as the following equation. The number phi is called the golden ratio. Now I will let my colleague Mara talk about it.
Thanks, Medea. We're going to make a little interpolation about the golden number because we found it quite interesting. The value of phi, also called the golden mean, the golden number, or the golden section, is approximately 1.61. It is the ratio of a line segment cut into 2 pieces of different lengths, such as the ratio of a line segment to that of the longer segment is equal to the ratio of the longer segment to that of the shorter segment. The origin of this number can be traced back to Euclid, who mentions it as an extreme and mean ratio in his famous book Elements. Basically, letting the length of the shortest segment be 1 unit and the length of the longer segment be x units, we get the equation that Medea actually mentioned before, x squared minus x minus 1 equals 0, for which the positive root is, surprise, surprise, the golden ratio. The ancient Greeks recognized this dividing or sectioning property, a phrase that was ultimately shortened to simply the section. It was more than 2,000 years later that both ratio and section were designated as golden by German mathematician Martin Ohm in 1835. The Greeks also had observed the golden ratio provided the most aesthetically pleasing properties for the, proportions for the side of a rectangle. Thus, the golden rectangle was born. It is a rectangle whose sides are, of course, in the golden ratio. We could build this aforementioned shape by using the Fibonacci numbers as well as sizes for the square units. So as seen in the figure to the right, we can start adding squares and keep adding squares as long as each new square has a side which is as long as the sum of the last two squares' sides. So 1 + 1 is 2, 1 + 2 is 3, and so on. If we draw a spiral with the starting point in the first square, which is made of a quarter of a circle in each square, we get a pretty accurate representation of, or approximation of, a shape often found in nature, architecture, music, and a lot of other fields. The spiral in the squares makes a line with the center of the spiral increased by a factor of the golden number in each square, as seen in the figure below.
Now we will go back to our problem. So for our Fibonacci sequence, which was xn plus 1 is equal with xn plus xn minus 1, where n was greater or equal than 1, we will have the equation that we already showed. We annotate Cn is equal with xn minus 1, the number of pairs of children at step n, and an is equal with xn, the number of pairs of adults at step n. So we rewrite our Fibonacci sequence as the following matrix, where n is greater or equal than 1. Now I will let my colleague George talk about the general case.
Thank you, Medea. Now we'll consider a more general case, a more realistic one too. Let capital D be the rate of mortality of the adults, D the rate of mortality of children, P the rate of reaching maturity, and B the fertility rate of the adults. We want to find out AN, the number of adults at the nth month, and CN, the number of children at the nth month, for all n greater or equal than 1. Firstly, we may observe that an plus 1 equals 1 minus capital D multiplied by an plus b multiplied by cn, and cn plus 1 equals b multiplied by an plus 1 minus d minus b multiplied by cn for all n greater or equal than 1. These two equations may be translated in the following matricial system for all n greater or equal than 1. We will now have A, the following matrix, and xn equals an cn. So xn plus 1 equals a multiplied by xn for all n greater or equal than 1. By mathematical induction, we obtain that xn plus 1 equals a to the power n multiplied by x1 for all n greater or equal than 1. The equation shows us that, knowing how to determine a to the power n, we can easily find out xn. Now, we will present a mathematical method to find the general formula for a to the power n. We will now work with eigenvalues. Let lambda 1 and lambda 2 be the eigenvalues of the matrix A, which can be easily determined as the solutions of the equation x squared minus trace A multiplied by x plus the determinant of A equals 0. We shall prove the following theorem: a to the power n equals lambda 1 to the power n multiplied by b plus lambda 2 to the power n multiplied by c if lambda 1 is different than lambda 2, and lambda 1 to the power n multiplied by b plus n minus 1 multiplied by lambda 2 to the power n minus 1 multiplied by c if lambda 1 equals lambda 2, where b and c are two square metrics that can be determined by cases n equals 1 and n equals 2. We may observe that matrix A checks the following relation: a squared minus the trace of A multiplied by A plus the determinant of A multiplied by I2 equals O2. If we multiply the relation above with A and A to the power n minus 1, we will obtain that A to the power n plus 1 minus the trace of A multiplied by A to the power n plus the determinant of A multiplied by A to the power n minus 1 equals O2. From this, we may conclude the following equation. Considering a to the power n equals an, bn, cn, and dn, in relation 1, we'll obtain the following system of equations for all n greater or equal than 2. All of them can be translated to a single recurrence relation: xn plus 1 equals the trace of a multiplied by xn minus the determinant of a multiplied by xn minus 1 for all n greater or equal than 2. The characteristic equation is lambda squared minus the trace of a multiplied by lambda plus the determinant of a, which is equal to 0. So we'll have two cases. If lambda 1 is different than lambda 2, we'll have the following system of equations. Thus, a to the power n equals lambda 1 to the power n multiplied by b plus lambda 2 to the power n multiplied by c. If lambda 1 equals lambda 2, we'll have the following system of equations. Thus, a to the power n equals lambda 1 to the power n multiplied by b plus lambda 1 to the power n minus 1 multiplied by n multiplied by c. B and c can be easily determined by the cases n equals 1 and n equals 2. Now let's see if you can predict how the population will end up based on the values of D, P, capital D, and B. Let an be the number of adults on day n and cn the number of children on day n. We may observe that xn equals an plus cn and the following equations. Therefore, the way the population changes from the day n to the day n plus 1 is determined by the relation of an multiplied by b minus capital D minus d multiplied by cn with 0. Applying the following changes, the formulas above are true for d different than 0. If d equals 0, the population will always grow. We notice that the relation an multiplied by b minus capital D minus d multiplied by cn with 0 is equivalent with the relation of b minus capital D divided by d with cn divided by an. To find out what happens after a very large number of days, all we have to do is compare the limit when n goes to the infinity of cn divided by an with b minus capital D divided by d. And we have three larger cases that are presented below. Now I will let my colleague Tudor to continue the solving of the problem.
Okay, thank you, George. Now to better visualize how the formulas above work, we created a Python program which, using the matplotlib library, draws our graphic for us. So here we have a function which multiplies two 2 by 2 matrices and returns the matrix in the variable c. After this, we set up the 4 parameters. So we have capital D, the adult mortality rate, P, the child maturization rate, B, adult fertility rate, and D, the child mortality rate. In this case, we took the Fibonacci example. And we note with n the number of months we want to see the graphic. Now, using the formula xn minus 1 equals with 1 minus d, p, b, 1 minus d minus p to the power of n minus 1 multiplied by 1, 0. To obtain the result for each step, we will have we'll assign the variable matrix to A, and we will memorize the result in the matrix B, which for beginning we have A1 equal with 1. So in the program in the right, we calculate 1000 steps for better accuracy of the results, and we memorize each result in arrays. So in array X, we have the total number of rabbits. In array A, we have the number of adults. In array C, we have the number of children. And in array Z, we have the ratio, Cn divided by An. After each step, we update the matrix B to the next step.
Now I'll take over from Tudor and explain the graphics. On the left part is the ratio children-adults, and on the right side are represented the dynamics of the rabbit population. In figure 1, we can observe them for the Fibonacci sequence. When capital D and D are 0 and B and P are 1, the ratio Cn divided by An equals 1 divided by 5, which tends to 0.6, and the population tends to plus infinity as shown on the screen. We can insert any values we want and observe how the graphic changes under different variables. When B is 0.3, P is 0.6, D is 0.2, and capital D is 0.4 with A1 equals 1 and C1 equals 0, Cn divided by An is greater than B minus capital D divided by D. Therefore, the rabbit population will tend to 0 because the number of adults will drop significantly. Here we have the following matrix for which A at the n power is equal with the formula shown on the screen. We can notice that the limit of C divided by A is equal with B minus capital D divided by D, which is 1. So the population will stabilize itself to 12, a positive value. For the last case, for the following matrix, for which A at the n power is the equation shown on our PowerPoint, the limit of C divided by A is smaller than B minus D capital D divided by D, so the population will grow to infinity. Now I shall let my colleague Ivana conclude our problem.
Thank you, Sabrina. So in conclusion, in this paper, we actually considered a more realistic model for the evolution of a rabbit population than the Fibonacci model, in which it took into account the mortality rates for the baby rabbits and adult rabbits, the breeding rate, as well as the maturation rate. The new model can be useful for predicting the number of rabbits after each month and the children-adults ratio. By varying the above rates, the dynamics of the rabbit population might change dramatically, from extinction of the species to the infinitely growing number of rabbits. We want to thank you all for paying attention.
You are now muted.
Hello everyone, so if you have any questions. Okay, so I saw the question, is this model very realistic? No, this model isn't very realistic because there can always be some natural disasters, like, I don't know, diseases that rabbits suffer, and we didn't take this in account. There are way too many variables possible to make this more accurate.
So thank you very much for that great presentation by the students of Yashi School. We will now leave you a minute to put some questions in the YouTube chat. We already have one. What happens if the Evenji values lambda d1 I are imaginary values? So
I may answer. So if the eigenvalues are imaginary, so the eigenvalues basically are the solutions of a second order equation, which is with real coefficients. So one will be the conjugate of the other one, and when we raise that to the power n by the new binomial, it will be a real number when we add up.
Thank you very much. We have another question. Is this model very realistic?
Yes, I already answered this question, sorry, but yes, there can be more variables to introduce and to make this more accurate. This only contains 4 variables, we saw them earlier. And I saw the other question for a much shorter term. We can modify the number of months for which we want to see the graph. So you can actually modify the n value from in the graphics we had n equal with 15 months. So we saw the result for 15 months, but you can actually see the result for any number of months you want.
Okay, thank you very much. Merci et bravo aux étudiants de Yash. On vous laisse voilà. Now we have another presentation by the students of Yash called The Roof is on Fire. Maintenant, on va continuer avec une présentation des étudiants de l'école de Yash qui s'appelle The Roof is on Fire ou, en français, Le toit est en feu.
Guten Abend, bonjour, good afternoon. We are really delighted to have the opportunity to be here. My name is Oana Ana Estera, and together with my colleagues, Rusu George Constantin, Mocanu Radu, Lefter Lucia Maria, Grumăzescu George Octavian, and Gal Stefania, we would like to present you the problem The Roof is on Fire. We are all students in the 11th grade at Colegiul Național Costache Negruțiv from Iași. With the help of our teacher, Adrian Zanoschi, and our researcher, Iulian Stoleriu from the Faculty of Mathematics, Alexandru Ioan Cuza, University of Iași, we concluded this research. We would like to start with a brief presentation of the conjectures and results obtained. A tourist is camping on the shore of a straight river. At a given moment, he finds himself at position A in figure 1, where he sees that the roof of his camping house, situated at position B on the same side of the river, is on fire. He quickly grabs an empty bucket and wishes to put down the fire with water taken from the river. He runs twice as fast with an empty bucket as with a full one. Where should he get the water along the river to minimize the total travel time to the house? Point B, the same problem as in point A, but this time the house is situated at point C on the other side of the river. Suppose that the swimming speed equals the running speed with a full bucket and the river water is calm.
First of all, we'll denote by S the place where the shore touches the river, by P the point where the man fills the bucket, and by V his speed of a full bucket. This means that his speed of an empty bucket will be 2V. So the time the man needs in order to cover the distance will be determined by the following equation. Knowing that V is constant means that we need to find the minimal value of AP plus 2PB. In this figure, let A1 and B1 be the projections of A and B respectively onto the line S. So the lowercase letter a will be the distance between A and A1, the lowercase letter b will be the distance between B and B1, and the lowercase letter d will be the distance between A1 and B1. We also denoted by x the distance between A1 and P, which means that the distance between P and B1 will be d minus x. So using the Pythagorean theorem, we came up with a function that will determine the time the man needs to get to the burning house, which means that the problem reduces to finding the minimum of this function. So what we did next was to find the second derivative of this function, which is strictly bigger than 0. This means that the derivative of f is strictly increasing on the closed interval between 0 and d. Since the derivative of f is continuous and the values of the extremes of this function are smaller and bigger than 0 respectively, it results that there is a unique point x0 in the closed interval between 0 and d such that the derivative of this function of x0 equals 0. Here we have a table of variations. We deduce that f attains its minimal value in x0, and after some calculations, we found a formula which is this one, where a, b, and d are given values and x is the only unknown value.
With the help of the C++ program, we have managed to draw out some particular values for a, b, and d in order for x to have a beautiful value. Here you may see some particular cases which have been reached by implementing the equivalent of the mathematical solution in C++ and by looking at the outcome that our program was giving. For a better understanding, I will present you the C++ programs. The C++ programs are a simulation of the mathematical solution. Basically, we iterate over all the possible solutions and retain the one with the minimal distance. We can easily do that since the computer can do lots of operations very fast. Some general facts that I would like to talk about before talking about each program are: first, we have included a new library called MATH.en.JEANS besides the basic one in order to be able to transpose the Pythagorean theorem in C++ by using sqrt, which is an abbreviation of square root. Second, the double data type, which we have used to declare some variables, allows us to work with real numbers. And third, the long number with which we have initialized the variable minim is the biggest number that the double data type can reach. Let's now get to discuss each program in particular. The first computer program reads the lengths a, b, and d of segments AA1, BB1, and A1B1, and the variable path in which we store the step. The program makes the point P move on the A1B1 segment from A1 to B1 with the step path, computing the distance AP plus 2PB and approximately determining the position of P in which this distance is minimal. The second computer program is similar to the first one. the only difference being that the lengths A, B, and D of segments A, A1, B, B1, and A1, B1 vary from 0, which is not included, to a maximum value, max A, max B, max D, respectively, with the steps PA, PB, and PD respectively. The variables PA, PB, PD, max A, max B, max D, and pass, which stands as the step for the point P on the segment A1, B1, are entered by the user. The program computes the minimum of the distances AP plus 2B, displaying it along with the position of P on A1, B1. Here you may see the outcomes of the programs.
What about the general case? So now we have to locate the point P where his speed of an empty bucket is k times his speed of a full bucket, which means that this time we have to minimize AP plus kPB. So this time the function is the following. It can be proven analogously that it attains its minimal point in x0, where x0 is the unique solution of this equation, derivative of function of x equals 0, which is the following.
At point B, P1 is the point on the shore S, where the tourist jumps into the river and begins to swim. If his swimming speed equals his running speed with a full bucket and the river water is calm, then the man saves the most time if the trajectory P1C is a straight line. Let the width of the river be W greater than 0. Let C1 and C2 be the projections of C onto the lines S and S prime of the shores of the river. Thus C1, C2 equals W. We expect that P1 is a point on A1, C1. And we denote, with the help of the Pythagorean theorem, that AP1 and P1C can be calculated. So the problem reduces to finding the minimum of this function. The computations are similar to those in the previous case, analyzed at point A, but the distance B from point B to the river is replaced by the sum W plus C. From the table of variation shown below, we deduce that G attains its minimal value only in x1, where x1 is the unique solution of this equation.
Okay, in the sequel, we consider the following three problems. Problem 1. If the speed of the tourist with an empty bucket or with a full bucket is the same, where should he get the water along the river to minimize the total travel time to the house? If the tourist has the constant speed v and p is a point on the shore of the river, then the time in which the man covers the distance AP plus PB will be AP plus PB divided by v. So t will be minimal if and only if the distance AP plus PB is minimal. Let B prime be the symmetrical of B with respect to the line S, and M be the intersection between S and AB prime. Since S is the mediator of the segment BB prime, both triangles MBB prime and PBB prime are isosceles triangles. Therefore, AM plus MB equals AM plus MB prime equals AB prime, and AP plus PB equals AP plus PB prime. But for all P different from M, the triangular inequality implies that AP plus PB prime is greater than AB prime. In conclusion, the optimal point is M.
Problem 2. Let A and B be 2 points located on an island at the confluence of 2 rivers. John has to go from A to the bank of the first river and take a picture, then to the bank of the second river and take another picture, and finish his route in B. Where should he reach the banks of the 2 rivers in order to cover a minimal distance? Solution. We construct the symmetricals A' and B' of A and B with respect to the rivers OX and OY. Then we conjoin A' and B' with a straight line that intersects the first river in M and the second river in M. We claim that the optimal trajectory is A, M, and B. Indeed, if we take arbitrary points P on OX and Q on OY and join them with the points A' and B', we will obtain a broken line that will be longer than a straight line A', B'. Using again isosceles triangles, this is equivalent to saying that the path APQB is longer than the path AM and B. Here we have different graphs with settlements of the points P and Q on the 2 banks. Problem 3. Let A and B be 2 points on opposite sides of a river. Suppose that the river has the same width everywhere. Where should a bridge be built such that the distance from A to B is minimal? Generalization from 2 points A and B separated by n greater or equal to 1 parallel channels. Solution. The length of any path from A to B contains the length W of the bridge PQ, which is the width of the river. So actually we want to minimize AP plus QB. In order to do that, we take a point B prime such that BB prime is orthogonal to the river and BB prime equals W, and we denote by M the intersection point of AB prime and the shoreline S. Thus, we get the bridge MN. We prove that it is the optimal one. Indeed, using the parallelogram MN/BB prime, we get that AM plus NB is equal to AB prime. For any other bridge PQ, AP plus QB is equal to AP plus PB prime, because PQBB prime is also a parallelogram. Since the shortest path between the points A and B prime is a straight line, the proof is complete.
For generalization, let A and B be separated by two parallel channels of width W1 and W2, with shorts denoted as in figure 9.1. The idea here is to calculate the minimal distance traveled by man on land. So let BB1 prime perpendicular on S1 with BB1 prime equals W1 plus W2. M1 be the intersection between AB1 prime and S1, and M1 N1 perpendicular on S1 with N1 on S1 prime. Now N1 and B are separated by only one channel of width W2. According to the first part of this proof, in order to cover the minimum distance between N1 and B, we have to build the second bridge the following way. Let BB2 prime perpendicular on S2, BB2 prime equals W2, M2 be the intersection between N1 B2 prime and S2, and M2 N2 perpendicular on S2 with N2 on S2 prime. We claim that the green path is the minimal distance between A and B in the conditions of the problem. Indeed, from the first part of the proof, we also have relation 2. On the other hand, since B1 prime, B2 prime, N1, M1 is a parallelogram, we obtain that M1 B1 prime equals N1 B2 prime. Therefore, relation 2 can be rewritten as relation 3. Let now another road from A to B, the blue one, which passes through points P1, Q1, P2, and Q2, as shown in figure 9.2. We want to prove that the blue path is longer than the green path. Indeed, let P2 prime on Q2 P2 behind P2 such that P2 P2 prime equals W1. Since P2 P2 prime P1 Q1 and P2 prime Q2 B B1 prime are parallelograms, we have this relation. And the lila broken line is longer than the straight line AB1 prime. By consequence, the optimal path is the green one. And here we summarize the way to build the two optimal bridges.
For a further generalization, we consider points A and B separated by n parallel channels. We use mathematical induction to find the places of the n bridges so that the path from A to B is minimal. We already discussed the case for two channels. Let's now see how we can pass from n-1 to n channels. As in the previous cases, the idea is to move the oblique segments using parallelograms so that they sit end to end. We will see that the green segments that make up the minimal path from A to B can be moved on a segment, namely AB1 prime. Also, the segments that make up any other route, we represent it here in blue, will lie on a broken line with ends in A and B1 prime. Let therefore point B1 prime so that B1 prime is orthogonal to the shorelines and B1 prime be the sum of the width of the n channels. Let M1 the intersection of AB1 prime with S1 and M1 the projection of M1 on S1 prime. Now points N1 and B are separated by n-1 channels, and by the inductive step we know how to build the bridges to ensure the minimal path. We claim that by using this construction, we also get the minimal path from A to B. Indeed, if we take point B2 prime on B1 prime B, so that B2 prime B is the sum of W2 to Wn, By the inductive step, we know that we can move the oblique segments on the line M1, B2 prime. And we get formula 4. Because M1, N1, B2 prime, B1 prime is a parallelogram, we can replace N1, B2 prime with M1, B1 prime, thus getting relation 5. Now, let's prove that any other route from A to B is bigger. We represent it here in blue a random trajectory. And since the bridges are common to the green and the blue path, we only need to show that the sum of the blue oblique lines is bigger than the sum of the green oblique lines. We do that by considering auxiliary points pi prime as we described them here. By doing this, we get some parallelograms, which allows us to move the blue oblique segments on the broken line A, P1 prime, P2 prime, Pn minus 1 prime, Pn prime, B1 prime, which is obviously longer than A, B1 prime. Recalling the fact that the sum of the green oblique segments is A, B1 prime, the proof is complete. Summarizing, if A and B are separated by n parallel channels, the way to build the bridges to ensure the minimal path from A to B is the following. We take point B1 prime, so that B1 prime is orthogonal to the shore lines and B1 prime be the sum of W1 to Wn. We intersect A B1 prime with shore S1 and we get M1, and we project it on S1 prime in N1. From now on, for any new step K, we consider point BK prime on B1 prime B's, with BK prime be the sum of WK to Wn. The head of the K's bridge is the intersection of NK minus 1 BK prime with shore SK, and the projection called MK, and the projection of it, MK, on SK prime is the other head of the bridge.
In conclusion, we have reached with the help of calculus in answering the questions, proposing the research, and having written a C++ code to approximate the solutions of the equation obtained, and to observe simpler particular cases, the following idea. We expect that if the speed with which the road is traveled varies in a more complicated way, the derivation of the equations will not be easy at all. In the sequel, we consider three related problems. By considering the speed of the travel constant, we were able to use a geometrical approach to solve them. Thank you for your attention.
You are now muted.
Are there any questions?
Thank you very much to the students of Yash. We will now leave the public a minute to write questions on the chat. Merci aux élèves de Yash pour votre présentation. On va maintenant laisser le public une minute pour mettre les questions en ligne. So we already have 3 questions. Have you thought about generalizing the program in space?
Well, we didn't think about it, but I guess it's really interesting. I mean, it would be a little bit more complicated, but yeah, we will think about it. I mean, we didn't actually take it into account, but we will.
Okay, thank you very much. Now for the second question. Could you work with the elementary algebra inequalities instead of calculus derivatives?
I think it would be quite difficult. I mean, we tried to use geometry for the first part, but we didn't actually get great results, and I believe that with the inequalities it would be really hard. But it might be a solution. I mean, just one, but maybe.
And third question, have you thought the other problems using a variable speed?
Yeah, well, for the first question, it's the first part of the problem. But then for the second and the third problems, they are a little bit more difficult. And since we didn't actually get the solution exactly for the easiest case, I guess the calculus would be really difficult to do for the second and third problem.
Thank you very much. Now we have a presentation called Keep the Distance by the student. So first we have a break till 4 o'clock. So see you then. Thank you very much. Hello everybody, welcome back. Now we're going to have a presentation called Keep the Distance by the students of Padova. Maintenant, on passe aux élèves de Padoue qui font une présentation qui s'appelle Keep the Distance ou en français Garder la distance. C'est à vous. Excuse me, do you have your microphone on because no one can hear you? Are you participating in the audio conference too? Hear you. Are you participating in the audio conference too? Hear you.
Can you hear me?
Okay.
Sorry. So do I have to restart?
Yeah.
Okay, sorry. Okay, so hello everyone. We are the Romano Bruni High School from Padua, and today we are presenting our problem, Keep the Distance. So this problem is about a sequence X of natural numbers, A, B, C, D, and we calculate the distances between them. So the result is a new quadruple sequence of natural numbers. By replicating the process S on the sequence, we get a third sequence, and proceeding in this way, we get a succession of quadruples of natural numbers. So can we predict the trend of the succession? Does it end in a fixed sequence or in a cycle? Do the answers change if we consider a sequence of 5 natural numbers? So here's an example, and you can see there's 4 natural numbers,
5, 9, 2, and 7. And below there are sequences with the distances between them. So we have 4 between 5 and 9, 7 between 9 and 2, 5 between 2 and 7, and 2 between 5 and 7. So we proceed in this way, and we get a final sequence with 4 zeros. So we found a theorem about this that says that each X sequence with natural numbers ends in a sequence with 4 zeros after applying the sequence for a finite number of steps. So here's the sketch of the proof that the maximum number in a sequence is weakly decreasing, and if it's not, it ends in a cycle. So the maximum number remains the same if and only there is a zero near it, and we analyzed the various cases where the zero appears in the sequence. So the zero remains for a finite number of sequences, and the succession ends in a sequence with 4 zeros in a finite number of steps. So we can see it below. The maximum is weakly decreasing, and the proof is that the absolute value of the distance AB is smaller or equal to the maximum that could be or A or B. So we can say that the maximum of the first sequence is smaller or equal than the maximum of the the maximum of the second sequence is smaller or equal than the maximum of the first sequence. So as I said before, there could be a zero in the sequences, and we analyze this sequence where some zero, where it could be 1 0, 2 zeros, or 3 zeros. So if some zeros could appear in the sequence, this is going to end after some steps. So in conclusion, if in a finite number of steps the maximum reaches the zero, then also the other numbers will be zero, and we can conclude that the sequence ends in a fixed sequence with 4 zeros. Now Luca is going to talk.
Can you hear me? Okay, so I'm going to start with 3 number sequences. We covered odd number sequences, but we focus on this type of sequence. So in this visual representation, you can see that each column represents a number. This wants to replicate the sequence before 0, 0, 0. Because when we reach 0, 0, 0, the sequence ends. However, in this case, you'll never have a sequence where each difference is the same, because as you can see, the difference between the first 2 and the second and the third one are equal. However, between the first and the last number, the sequence is 2 blocks, not 1. So this proves that it ends in a cycle. On a more mathematical approach, we consider 3 number sequences with numbers, of course. So we put 3 numbers in the first one, 1, 9, 37. And as you can see, just starting with the second one, the first 2 numbers together form the third one. So 8 plus 28 equals 36. And this goes with all the other sequences. We called it the theorem of the sum. Indeed, the smallest number are called addendums that combine together form the sum, which is in this case 36. So, as we said, the sequence with 3 numbers ends always in a cycle after applying s function for a finite number of steps. But how are cycles made in this type of sequences? Well, the theorem of the sum applies even in the cycle. So in this case, k plus 0 equals to k. So this is a cycle where two numbers are equal and there is a 0. And this goes on and on, as you can see, because at some point this 0 will move and the two numbers will still be equal. So we have to prove that in order to end a cycle, the smallest addendum must become 0. So it's slightly decreasing. But first, we analyze the other two numbers of the sequence, which are the sum and the greater addendum. The sum is strictly decreasing because sum minus the addendums gives the other addendum, so it will never be higher than that. And the same goes with the greater addendum, because the sum minus the greater addendum equals to the smaller one, and the difference between the two addendums gives a number with more than the original addendum. So even the greater addendum is strictly decreasing. Then we found out that the smaller addendum depends on the greater one. That's because if the ratio between the two is higher than 2 to 1, then the smaller one will not decrease. However, because as we said, the greater addendum decreases, at some point the ratio will be lower than 2 to 1. So we will reach a sequence where the smaller addendum has become 0. And if the smaller addendum has become 0, then the higher addendum must be the same as the sum. So we prove that it ends in a cycle. I will pass the microphone to Matilde.
Okay, hi. To conclude the presentation, here it is the next point of work. In order to predict the trend of the succession, we try to study starting from the end. Given a sequence, we try to understand which was the maximum length of succession that we could trace back. Here it is an example. If we have the sequence 7863, this is one of the possible previous sequence. So here it is what we have found since now about the backward succession. Let's start with the sequence A first, B first, C first, D first, whose the sequence before is given by A, B, C, and D. That is the sequence that we have to find. In this case, A first is given by the absolute value of A minus B, B first is given by the absolute value of B minus C, and C first is given by the absolute value of C minus D, and D first is given by the absolute value of D minus A. We put all these points in a system and we solve it isolating the variables. At the end, we obtain an equation that depends from A, which, as we can see, we can eliminate. So the condition that we obtain is plus or minus A first, plus or minus B first, plus or minus C first, plus or minus D first equal to 0. And we have to find the condition that satisfies the equation. Okay, to better understand, we made an example. If we take the sequence A first, B first, C first, D first equal to 1, 2, 3, and 4, the two possible solutions of the condition are 1 minus 2 minus 3 plus 4 equal to 0, and minus 1 plus 2 plus 3 minus 4 equal to 0. Now we can attribute any value to A because the system depends on it. As we can see, by solving the calculation, we obtain two sequences, 7, 8, 6, and 3, and 7, 6, 8, 11. So there isn't a unique possibility of sequence. We still have some unanswered questions about backward successions. we found a way to go back in the succession from a given sequence to a previous one, but we still don't know how much we can go back in the succession. We know that some sequences don't have a previous sequence, but we want to understand how many backward steps we can take in a succession. For example, in a given sequence, can we go backwards for 10 or 20 steps? For a sequence of 5 natural numbers, one of the questions that the problem arose was to study 5 natural number sequences. We decided to start with 3 natural number sequences because we thought it could be easier. We can predict that 5 natural number sequences and the 3 natural number sequences have the same trend, that is ending in a cycle. For even or odd sequences, we think that we can generalize what we have found about 3 and 4 natural number sequences. For even sequences, like for natural number sequences, they all end in a sequence of all zeros. And for odd sequences, like 3 natural number sequences, they all end in a cycle. But we still have to demonstrate these points. So that's it. Thanks for your attention and time.
Thank you very much for your presentation. We're going to give the audience a minute if they want to put any questions online. Merci beaucoup pour votre présentation, c'était vraiment super. On va maintenant laisser le public 1 minute pour mettre des questions en ligne. Okay, so we have one question. Have you calculated and compared the duration to get the null sequence?
Can you repeat, please? I didn't understand. Excuse me, can you repeat the question, please? I didn't understand, I'm sorry.
Okay. So have you calculated and compared the duration of the zero sequence?
Excuse me, can you repeat the question, please? I didn't understand. I'm sorry.
C'est bon, ça c'est vite.
Sorry, we still haven't calculated yet.
Okay, well, thank you very much for that great presentation by the students from the Hague. We will now leave. Non, no. Là, je fais la prochaine. Donc, okay, thank you. Now we are going to pass to the next presentation by called Who Can Win Millions by the School of Mestre. Magic Game. Attends, quoi? For the next presentation, we have a presentation called The Magic Game from The Hague. Pour la prochaine présentation, on accueille les étudiants de la Hague qui font une présentation qui s'appelle Magic Game, ou en français, un jeu de magie.
Hello, today we're going to show what we have discovered about this magic trick.
The contents of this presentation are a small introduction to myself and my teammates, outlining the magic trick, a short video, our first solution, the magic trick using base 3, and finally a conclusion to summarize everything we've talked about during this presentation.
We are students from the European School The Hague, ESH, and are in the first and second year of secondary. Our names are Francesco,
Leontine,
Alexander,
Maxine.
Today we would like to present a magic trick together with all the math behind it.
These are the steps towards performing the magic trick without the answers for now. Two people have 27 cards. A person chooses one of those cards without revealing it, and then turns it to the pile of cards. The second person now has 3 rounds to find this card. Each round is made up of 3 stages. He deals the cards in 3 piles face up. He asks in which pile the card is. He reforms a pile by stacking the 3 piles in the order of his choice.
Before we go into any more detail, here is a small video to demonstrate the magic trick.
So hello everybody. So today I'm going to show you the magic trick. Here are my 27 cards and they're all different. And he's going to pick a card and I'm going to find out the card. So here's the first step. I'm going to find out the cards and you have to pick. Don't show it to me and show it to them. Okay, now put it here. Now I'm gonna make 3 piles, and you're gonna have to tell me which pile it is in. Which pile is it in?
I think this one.
Check. Is it this one?
No. Yes.
Okay. Perfect. Now I'm gonna do it another 2 times. So. Which pile is it? This one? Okay, last time. Which one is it? This one?
Yeah.
And is this your card?
Yes.
The first solution. You start with a full pack of cards, 54 in total. By splitting the pack in two, you should get two smaller piles of 27 cards. Put one to the side and keep the other one in front of you. If it isn't already, flip the pack of cards so that it is face down. Then fan out the cards in such a way so that another person can pick one. Look at it without revealing it, and put it back from where it was taken. Make sure the person has remembered his or her card, and then flip the pile face up, and share the cards into 3 piles, from left to right. While you do so, ask the person with you, the one who memorized the card, to look carefully at each card being shared. Then, after all cards have been shared, ask the person to tell you in which pile their card is. Take the pile with the appointed card and put it over the two still face up. Share the card again, still face up. Then, like before, ask the person with you to tell you in which pile their card is. Flip all the piles, take the pile with the card, and put it over the other two, face down. Share them again. Flip each card individually as you share it, so that it is face up. Take the shown pile and take the last card, and that should be the chosen card.
Base 3. Before going on into any more detail, we would like to make sure you know what base 3 is. The base we always use is base 10. This means that the numbers from 0 to 9 in our everyday life are what make it up. These numbers can be arranged and rearranged to give endless possibilities of numbers. Base 3 is almost the same. The only numbers used there are 0, 1, and 2. To transform a number into base 3, you have to see how many times powers of 3 fit into that number. We can make that easier by constructing a table. As is visible, the top of the first column to the left contains the number 3 to the power of 4. The next one has 3 to the power of 3, then comes 3 to the power of 2, 3 to the power of 1, and finally 3 to the power of 0. To make it even simpler, we have put the actual number resulting from these powers next to the table. Now, suppose you want to transform the number 8 into base 3. You look at the table. How many times does 3 to the power of 4 fit into 8? None. You put a 0 under the column of 3 to the power of 4. Does 3 to the power of 3 fit? No. You write another 0 under the next column. You write one more 0 in the next column, as 3 to the power of 2 does not fit into 8 either. But then you see 3 to the power of 1. That fits 2 whole times into 8. So you write a 2 under the designated column. 8 minus 3 to the power of 1 is 5, and by subtracting that again, you get 2. You go to the next column. 3 to the power of 0. That also fits twice into the remaining number. The number you get is a number in base 3. In this case, 8 in base 3 is 22. Now that you know how to transform a number into base 3, let's see how it works with the magic trick. You start in the same way as a normal magic trick. Take a pack of 54 cards and split it into 2, so you have 27 cards in each pile. Put one half away and keep the other. Now, before you do anything else, ask the person with you to choose any number between 1 and 27. Once that number has been chosen, transform it into base 3. Suppose the chosen number was 8. We already know that 8 is 0 to 2 in base 3. It is important that your number in base 3 has 3 digits. If If it doesn't, add 1 or 2 zeros in front of it as we did with 22. Now flip the number in base 3 so that it is backwards. Remember this number well, you will need it later on. Now give your pile to the person with you and tell them to flip the pile so that it is face up, and then to find the 8th card from the top, since that was the number between 1 and 27. Now give 27. While this is being done, close your eyes or look away. Tell the person to do 2 things. The first thing they have to do is to make sure that the card is going to be back in the same position as before and in the same direction. The second thing they should do is remember the 8th card very well. Now look at the pile of 27 cards and take them back. Now put them into 3 piles of 9 cards. Now each pile is going to get a number, 0, 1, or 2. As you can see, the number, the code 220, it was originally 022, but we flipped it, correspond to the numbers in the piles there. This is because the numbers in the piles are the numbers that make up base 3. 0 is at the bottom, 1 is in the middle, and 2 is at the top. You think of the first number in the code, which in this case is 2. Then take the appointed pile and make sure it ends up at the very top, since the pile number 2 is at the top. The other 2 piles can go under in any order. Now, you put the piles in the order that you have and make sure you have one big pile that is, again, face down. This time when you share it, you flip each card individually as you take it. This means that you will end up with 3 piles face up again. As before, you ask the person in which pile their card is, and then you think about your code. The first part of the code has been used, therefore you can't forget it. The next number in the code is 2. Therefore, the appointed pile will be put in position 2. Also like before, the others will go in any order underneath. This time, after you have put all 3 piles on top of each other, you flip the pile so that it is 3 piles face down. Now, you put the piles in the order that you have and make sure you have one big pile that is, again, face down. This time when you share it, you flip each card individually as you take it. This means that you will end up with 3 piles face up again. You think of the last number in the code. In this case, it was 0. You put the appointed pile in the pile of 0, and then you take the 8th card from the top. The 9th card should then be the chosen one.
Conclusion. During this presentation, you have seen what we have discovered. We have found 2 main ways to do the magic trick and many more minor ways to do it. We also have found how to incorporate base 3 into the magic trick. We know that the magic trick can work with a different number of cards, but we didn't find any visible or obvious patterns. The one thing we do know for sure is that you need at least 2 piles when you distribute the cards. We hope that you learned something new from our presentation and that you have enjoyed it. Thank you for listening.
You are now muted.
Thank you very much for that interesting presentation by the students of the HAG. We will now leave the public a minute to put some questions in the YouTube chat. You have a slide on presentation. Would you like to share what's on it?
No, it's not for this presentation, the slide.
Oh, okay. Well, there are no questions, except for one, but do you speak English? I mean, yes. Well, thank you very much. Now for the next presentation, we will be welcoming the students from the Mestre, and their presentation is called Who Can Win Millions? Pour la prochaine présentation, on accueille les élèves de Mestre qui présentent un problème qui s'appelle Qui peut gagner des millions?
You are now muted.
You can now start your presentation.
Yes, can you hear me? Yes, okay. Today we are faced with this problem that says vous choisissez des entrées positives à votre guise pour que leur somme soit égale à 1000. Vous gagnez un montant égal au produit des nombres choisis. Serez-vous être très riche? Our task is to find the maximum possible value to understand if it is actually possible to become a millionaire. After multiplying a certain amount of numbers, whose sum is equal to 1000. We used some different methods. Can you put the other one? We used some different methods, and through some researches, we made 3 initial considerations. The first one, we considered 2 numbers, n and k, natural positive, and we started with the Excel this function that is written here. Then we decided to consider not only the case of the sum 1000, but to make a more general study where the sum is a natural number n that is positive and natural. Lastly, we decided to consider every possible cases in which the fraction x over n is also an irrational number. So we consider every possible case. We started by studying the first natural numbers by writing all the possible decomposition and calculating which one gives the highest product. We excluded 0 since any number multiplied by 0 gives 0 as a result, and 1 because it is the neutral number of multiplication. Starting from the table with the studied numbers, we made some observation. As we can see,
the numbers from 5 onwards are less than the product of their addends. So using a number greater than 5 as an addend will never be convenient because it can be replaced by the sum of its addend, thus giving a greater product. The most convenient thing is to write the numbers as the sum of 2, 3, and 4, and using 2 plus 2 or 4 makes no difference because the product is still 4. The best result is obtained when the addends are all or almost the same, and if both 3 and 2 can be used, 3 gives a better result. Finally, looking at the table, you can see a certain repetition in the best decomposition that depends on the rest of the division by 3 of the considered number. For this reason, to study the numbers, we have decided to divide them into 3 classes.
So first, let's prove statements 1, 2, and 3. Reading the theorem 1, let n be positive integer. For every n greater than or equal to 5, there are p and q positive integers such that p and q are smaller than n, and their sum is equal to n. So in this case, it's convenient to distinguish 2 cases, where in the first one we consider n even, while in the second we consider n odd. In this case, so n can therefore be rewritten as 2m in the case of even, or 2m plus 1 in the case of odd. So in the case of hidden, we can see this inequality. 2m is smaller than m squared. And whose solution are m smaller than 0 or m greater than 2. So in the case of n even, the theorem is true if n is greater than 4. While in the odd case, we can see this inequality where 2m plus 1 is smaller than m times m plus 1, whose solution are m smaller than 1 minus square root of 5 over 2, or m greater than 1 plus square root of 5 over 2. In this case, since we are dealing with a positive integer n, it's convenient to approximate the value found to the integer. So in the case of n odd, the theorem is true if n is equal or greater than 5. So, for example, we consider 15, and following the previous reasoning, it can be decomposed as 8 plus 7, which in turn can be decomposed as 4 plus 4 plus 4 plus 3. What about the corollary? So by theorem 1, if n is greater than 4, n can be replaced by 2 numbers that are minor than n itself. And by iterating the procedure is created a sequence of positive integers that will end in a finite number of steps. Therefore, we will certainly have, as we have shown, that the minimum sequence of positive integers will be formed by the number 2, 3, and 4. In this case, we have 2 and 3 because 4 can be written as 2 plus 2, and it's given as 2 times 2 is equal to 4.
And about assumptions 5 and 6, we got that having a key, a natural number key, k, and x as the initial number, x can be considered as the sum of all the x. We've got that P, the product of all the k addends is the maximum just in the case that all the k addends are all the same, and this can be proved. And also there's also the third theorem we used that says
that if the natural number we use as an initial number is a multiple of 3, then the maximum can be reached only when the k addends are all equal to 3. And in fact, as we can see here, if n is equals to 3m, and if n is even, by theorem 2 we can say that n equals to 3m and it equals to 3 plus 3 plus 3 m times. Then p is just 3 at the m at the power of m. Since n is even, we also have that n equals to 2 plus 2 plus 2 plus 2 at a number L of times, and so we have that p equals to 2 at the power of 3n over 2. In such a case, however, we have that 3 at the power of m is greater than 2 at the power of 3m over 2. This because if we apply the function of logarithm, we have that m per m logarithm of 3 is equals to 1, and it's greater than the logarithm of 2. And so we divided all the numbers in 3 categories. The first category is comprehends the numbers that are multiples of 3, and in this case we just analyze this case because as we can see in the third theorem, the maximum is obtained when x1, x2, x3 are all equal to k, to 3, and so it's obtained by key equal to m, and okay. In the second category comprehends the numbers n that equal to 3m plus 1, and in this case the maximum product is obtained with a key k that is equal to m plus 1, and so we have all we have m minus 1 3, and we have just 1 2 in the product. However, in the third category we have the numbers that are equal to 3m plus 2, and in this case as we saw before, we have m3, but we also have 1 4, or as we saw before, 2 2 because adding 2 or 2 2 or 1 4 is the same.
I'm so sorry to but we can't hear you. But we can't hear you.
Mi sentite? Sentite? Okay. Okay, at the beginning, we told you that Excel can be an excellent tool to observe hidden links. In this table, you can see how we have calculated not one, not 10, but every single product. On the right, you see a confirmation of what my companion have already told you. The maximum is made up of factors equal to 3 as much as possible. But it was not enough for us because we wanted to go further. For this reason, you can see in the table on the left, we have calculated the maximum of our function, even accepting rational x over n values. What we have discovered is amazing. The maximum value is obtained when the ratio x over n is the number of neighbors, or e. To be precise, we should say that the product is defined by the function is divided by n, or raised to x. X and n continue to be natural numbers, and the truth is that as x tends to infinity, the ratio tends to e. Okay, look at this graph. You can see that when x is about 350, the curve goes up a lot and then goes down quickly. What we want to do is show that the maximum point is strictly linked to the number of neighbors. And now I will explain how we did it. Okay, first we have to write our function in a smarter way, as you see here. Then we have to calculate the first derivative. Here you can see all the steps. For those who don't know, the maximum is found by setting the derivative equal to 0. And so we did. With some elementary passages, it's possible to highlight that the maximum of the function is strictly linked to e. We are done. In Italian, we say CVD. But now we have to answer the initial question: can we become millionaires? Well, the answer is no. If we choose carefully how to divide 1,000 in the way we have explained to you, not only we would become millionaires, but we would become the richest people in the world. Sorry for that problem. I finished. Thank you.
Thank you very much and well done for that great presentation by the students of MATH. We will now leave the public a minute so we can see if there are any questions. Merci et bravo aux étudiants de Metz. On va laisser le public une minute pour qu'ils puissent poser des questions. Okay, so there's no questions, so now we can pass to the next presentation. For the next presentation, we are welcoming the students from Yash. Their presentation is called Decomposing Integers. Pour la prochaine présentation, on accueille les élèves de Yash qui présentent un problème qui s'appelle Decomposing Integers.
You are now muted.
Okay, you can now start your presentation. Good luck.
Thank you.
Thank you. Hello, my name is Gross Alexandru.
And I am Lucanu Sebastian, and our teacher is Kulak Tamara.
And today we are going to present decomposing integers. So the quote is, God created the integers, all else is the work of man, said by Leopold Kronecker, who was a great mathematician. The problem. What are the integers that can be written as x squared plus ay squared, where a integer is fixed? Remark. Finding an integer that can be written as x squared plus ay squared is like looking for an integer for which the equation x squared plus ay squared equals n has solution x and y integers. It will be noticed that some equations have no solution, while others have a finite number of solutions, and others have an infinite numbers of solutions. Using the scientific workplace program for graphing, we will analyze the important cases a equals 1, minus 1, 2, and minus 2, discovering the solvability of equation by graphical search on circles, ellipses, lines, and hyperboles. For a equals 0, we will also mention the graphical answer. We will present some general results demonstrated in number theory, which are found in the works in the bibliography, both for a1, 2, minus 1, minus 2, 0, and for other values. We will also mention open problems. A computer program could be written to generate for each fixed a integer the numbers n equals x squared plus ay squared integer, giving values x and y positive integer, and then ordering the generate integers having an infinite number of integers. The program must be stopped running, imposing an upper generation limit.
So the first case, when a is bigger than 0 for 1, 2, 3, 5, 7, and other cases. The first question for a equals 1. What are integers that can be written as x squared plus y squared? Solution. Since x squared plus y squared is bigger or equals to 0 for any x and y with integer, for n integer n smaller than 0, it cannot be written as x squared plus y squared with x and y integer. We will look for n integer n bigger or equal to 0 for which there is x and y integer such that n equals x squared plus y squared. The first answer. We partially researched by graphical analysis and algebraic verification which of the numbers from 0 to 21 can be written as x squared plus y squared. The first case, when n is 0, we are looking if the circle that becomes a double point with the equation x squared plus y squared equals 0 if and only if x and y are 0 passes through a point with integer coordinates. We find that n equals 0, which also equals 0 squared plus 0 squared. And for n integer and n bigger or equal to 1, we are looking if the circle with the center 0, 0 and radius square root of n with the equation x squared plus y squared equals n passes through a point with integer coordinates. By searching for n from 1 to 21, I just looking for the colored circles passing through integer coordinate points, we find all possible writing solutions. The red circle, which is represented by the value 1, can be written as 1 square plus 0 square, can also be written as 0 square plus 1 square, can be written as minus 1 square plus 0 square, and can be written as 0 square plus minus 1 square. The orange circle, which represents the value 2, can be written as 1 square plus 1 square, can be written as minus 1 square plus 1 square, can be written as minus 1 square plus minus 1 square, and can be written as 1 square plus minus 1 square. The yellow circle, which is representative of the value 3, cannot be written as x squared plus y squared. Thus, there are no integer coordinate points x and y located on the circle with the center 0, 0 and the radius square root of 3. We also, each of the circle represents a different value that we studied, and our graphic conclusions is that for n from 1 to 21, completely traversing the circles of equation x squared plus y squared equals n, curves with finite length, from the point square root of n 0 counterclockwise, we found that the numbers 1, 2, 4, 5, 8, 9, 10, 13, 16, 17, 18, and 20 can be written as x squared plus y squared with x and y both integers. The second answer in the theorem in number theory. By Fermat, the prime number n equals p bigger than 0 is written as p equals x squared plus y squared with x and y both integers, if and only if p equals 2 or p equals 4k plus 1 with k positive integer. P congruent 1 modulo 4. And b, the number n, which is an integer with n bigger or equal to 1, is written as n equals x squared plus y squared with x and y both integers, if and only if its prime factors of the form 4k plus 3 with k positive integers are numbers that appear at even powers. The first remark. If n equals k squared with a k integer, then there exists the trivial writing solution n equals k squared plus 0 square minus k squared plus 0 square, or 0 square plus minus k square, or 0 square plus k square. The second remark. If there are two distinct unordered pairs of solution x and y both positive integers of the equation x squared plus y squared equals n, then n is composite. The third remark, we studied a special case of Pythagorean numbers using the complex numbers. And here are our results. The second question, when a equals 2, what are the integers that can be written as x squared plus 2 times y squared? Solution. Since x squared plus 2 times y squared is bigger or equals to 0 for any x and y integer, when n is an integer and it's smaller than 0, it cannot be written as x squared plus 2 times y squared with x and y both integers. We look for n integer with n when n is bigger or equal to 0, for which there is x and y integers such that n equals x squared plus 2 times y squared. The first answer. We partially researched by graphical analysis and algebraic verification which of the numbers from 0 to 21 can be written as x squared plus 2 times y squared. The first answer, when n equals 0, we are looking if the ellipse that becomes a double point with the equation x squared plus 2 times y squared equals 0 if and only if x and y are both 0, passes through a point with integer coordinate. We find that n equals 0, which also equals 0 squared plus 2 times 0 squared. 2, when n is integer and n is bigger or equals to 1. We are looking if the ellipse with the center 0, 0 and the semi-axis square root of n and square root of n divided by 2 with the equation x squared plus 2 times y squared equals n passes through a point with integer coordinates. By using the same methodology as when a equals 1, we obtain each ellipse determines an value, and by searching for a number from 1 to 21, it is looking for the colored ellipses passing to the integer coordinate point. We find all possible writing solutions. Graphic conclusions. For n from 1 to 21, completely traversing ellipses of equation x squared plus 2 times y squared equals n, curves with finite length, from the point square root of n 0 counterclockwise, we found that the numbers 1, 2, 3, 4, 6, 8, 9, 11, 12, 16, 17, 18, and 19 can be written as x squared plus 2 times y squared with x and y both integers. The second answer, in the theorem in number theory, by Lagrange, the prime number n equals p, which is bigger than 0, is written as p equals x squared plus 2 times y squared with x and y both integers. If and only if p equals 2 or p equals 8k plus 1 when k is positive integers, p congruent 1 modulo 8, or p equals 8k plus 3 with k positive integers, and p congruent 3 modulo 8. And b, the number n, which is an integer and is bigger or equal to 1, is written as n equals x squared plus 2 times y squared, with x and y both integers, if and only if its prime factors of the form 8k plus 5 with k positive integers, or 8k plus 7 with k positive integer, congruent with 5 modulo 8 or 7 modulo 8, are numbers that appear at even powers. The first remark, if n equals k squared with k integer, then there exists a trivial writing solution n equals k squared plus 2 times 0 squared, or minus k squared plus 2 times 0 squared. So by using the same methodology, we also studied the cases 3, 5, and 7. By graphical analysis, we found that for n equals 0, when 0 equals 0 squared plus a times 0 squared, for n from 1 to 21, completely traversing ellipses of equation x squared plus a times y squared equals n, from the point square root of n 0 counterclockwise, we found that the numbers, we found these numbers can be written as x squared plus a times y squared. Here are the graphs for each of the cases. We also use the theorem in number theory for prime numbers, and this is what we obtained. The fourth question, for a certain a bigger than 0, what are the integers that can be written as x squared plus a times y squared? We couldn't determine by graphical analysis and algebraic verification, since it would be too difficult for larger values of a bigger than 0 and n bigger than 0. And here we also wrote special cases for prime numbers. And a remark here is that if n equals k squared with k integer, then there exists the trivial writing solution n equals k squared plus a times 0 squared, or minus k squared plus a times 0 squared.
So, in the second case, we have a smaller 0. Then 0, a equals -1, -2, other cases. Question 1. When we have a equals -1, what are the integers that can be written as x squared minus y squared? Solution. We look for n integer for which there is x and y integer, such that n equals x squared minus y squared. For for the first answer, we partially research by graphical analysis in a certain region of the plane and algebraic verification, which of the numbers n equals minus 21, minus 2, minus 1, and so on to 21 can be written as x square minus y square. In the first case, n equals 0, we are looking if the hyperbola that becomes 2 second lines with the equation x equals y or x equals minus y passes through a point with Pythagoras coordinates. And we find that n equals 0 equals plus minus x square minus plus minus x square equals plus minus x square minus minus plus x square, whatever x integer. So in the second case, we have an integer greater than and equal to 1. We are looking if the hyperbola with center 0, 0 with the equation as shown here passes through a point with integers coordinates. So by searching for n1 to 21, that is looking for the colored hyperbolas passing through integer coordinates points, we observe only some of the possible writing solution rows from the studied plan region. So we have the red line where 1 is equal 1 square minus 0 square. Also minus 1 square equal minus 0 square. The orange line 2 equal, we cannot decide from the study. 3, the yellow line 3 equals 2 square minus 1 square, minus 2 square minus 1 square, and minus 2 square minus minus 1 square, and 2 square minus 1 minus 1 square, and so on. And in the first case, in the third case, we have an integer that is smaller and equals minus 1. And we have the same method and similar graphics with hyperbolas here. So for the graphic conclusion are 1, n equals 0 equals plus minus x square minus plus minus x square equals plus minus x square minus minus plus x square, whatever x integer. For n to 1 to 21, partially traversing hyperbolas of equation, x square minus y square equals n, curves with infinite length, from the point square root n 0 in the lower left to the upper right direction, we find the numbers, that numbers 1, 3, 4, 5 to 21 can be written as x square minus y square, x and y integers. In addition, the writing is not unique due to the symmetry. It is sufficient to find the solution, x and y positive integers for the equation x square minus y square equals n. Ideas of those points on O x, O y, or in the first quadrant that are on the hyperbola and have coordinates in. And for n minus 21 to minus 1, we have these numbers. So the second answer, we use theorem in number theory. The integer is of the form 2k plus 1 k integer and congruates 1 modulo 2 or 4k and congruates 0 modulo 4. Then n can be written as n equals x squared minus y squared. If n is an integer is of the form 4k plus 2 and congruates to modulo 4, the question remains open. Here's a sketch of proof. We look for an integer for which there exists x and y integers such that n equals x minus y, x plus y. So whatever n 2k plus 1, it will exist x equals k plus 1 and y equals k integer, such that the condition is true. But if we have this condition that whatever n equals 4k plus 2, the question remains open. We try, but x equals 2k plus 3 divided by 2, and it's not integer, and y is 2k minus 1 divided by 2, and is not integer. And the first remark, if n equals k squared, then there exists the trivial writing solution that n equals k squared minus 0 squared equals minus k squared minus 0 squared. And if n equals minus k squared, then there exists a trivial writing solution that n equals 0 square minus k square or minus square. In the second question, we have that a equals minus 2. And we have that what are the integers that can be written as x square minus 2y square. We look for an integer for which there is x and y integer, such that n equals x integer minus 2 integer, y integer. We partially research by graphical analysis in a certain region and algebraic verification which of the numbers n minus 21 to 21 can be written as x square minus 2y square. So we have also the same case if n equals 0, and we have this hyperbola for the second case when n is an integer and greater and equal to 1. Also, the graphical analysis area must be enlarged as a region in the plane to find at least one solution for the writing n. If it exists using x and y integer coordinates, here we will increase the symmetric region of the plane, minus 5, 5, minus 5, 5, only partially relative to 0x, 0y, and the first quadrant. It has to 0, 12, 0, 12, symmetrizing then the solution found. And here are the values we found. Also, here's the third case that we studied when n is smaller and equals to minus 1. Also, here we have a graphic. So the graphic conclusion is that n equals 0 square minus 2 0 square. And for n 1 to 21, we have obtained this number. And for n minus 21 to minus 1, we have obtained these numbers. So the second question, we use theorem in numbers theory that the odd prime number n equals p greater than 0 is right, and as shown here. and if only and only if p equals 8k plus 1, and k is a positive integer, p congruates 1 modulo 8, or p is 8k minus 1. P congruates minus 1 modulo 8. And so the prime number n equals minus p is smaller than 0 is written as minus p equals x squared minus 2y squared. If only and only if p equals 2 or p congruates plus or minus 1 modulo 8. So the first remark we have that if n equals k square, then there exists a trivial writing solution. N equals k square minus 0 square, or minus k square, or if the minus k square, we have that 0 square minus k square, or minus k square. Here we use the Bell equation for that the equation x square minus 2y square minus 1 has an infinity of integer solution, and we show why here. Question 3. We have certain a smaller than 0. What are integers that can be written as x square plus ay square? And the answer is graphical analysis and algebraic verification become difficult for large values of a greater than 0 or and n greater than 0. So for the prime number n equals p greater than 0, we have these results, and we use the theorem in number theory that is writing the prime numbers as this form written here, and for the other slides, we have the Bell equations studied by Andreescu, and here are the sketch of proofs and what we studied.
So for our third case, when a equals to 0, for a minus 1, what are integers that can be written as x squared plus 0 times y squared? Since x squared plus 0 times y squared is bigger or equals to 0 for any x and y defined in z, when n is integers and n smaller than 0, cannot be written as x squared plus 0 times y squared, x and y in both integers. We look for an integer which is also bigger and equal to 1, for which there is x and y integers such that n equals x squared plus 0 times y squared. We used the same methodology for the other. We partially researched by graphical analysis in a certain region of the plane and algebraic verification which of the numbers from 0 to 21 can be written as x squared plus 0 times y squared. Here is the graph. And here are our answers. And our graphic conclusion is that for n from 1 to 21, partially traversing h lines of equations x squared plus 0 times y squared equals n curves with infinite length from bottom to top the direction, we found that the numbers 1, 4, 9, and 16 can be written as x squared plus 0 times y squared, with x and y both integers. And here is the bibliography we use for the theories for the theorems in the number theory. Thank you for your attention.
Thank you for your attention.
Thank you to the students in YASH for your presentation. It was great. We will now give the public a minute to write their questions in the online chat. Merci aux élèves de YASH pour votre présentation. On va laisser une minute au public pour qu'ils puissent poser leurs questions dans le chat. Your presentation was great, but we don't have any questions in the chat. So I think we will pass to the next presentation. Now we're going to have a presentation on irrational numbers by the students of YASH. Maintenant, on passe à la prochaine présentation par les élèves de YASH pour leur présentation sur les nombres irrationnels. Thank you very much. Goodbye.
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 C'est eux qui gèrent.
You can now start your presentation on irrational numbers for ASH school. Welcome, you can now start your presentation and good luck.
Okay, see.
Hello, I'm Stefan.
Hello there, I'm Alex.
Hello, my name is Matej.
Hello, I am Bogdan.
Hello, I'm Yulia.
We are all students of the National College YASH, and today we'll present our solution to the problem irrational numbers. This year, our teacher was Gabriel Popa, and our researcher was Professor Claudiu. In this presentation, we'll talk about the problem statement, our solution, a bit of generalization to the problem, and we have also some conclusions.
Here is our problem statement. Let g, who is n equal to 1, be an integer. Determine all numbers of the form a plus b square root of g such that their inverses are of the same form. We assume that d is a square free, where d cannot be 0 and 1, and d is not divisible with the square of any prime. Therefore, d can be 2, 3, minus 1, 6, but not 8 or 18. For example, for d equals 2, 1 plus square root of 2 has this property, shown below. The basic idea of this problem is that d is an integer, which is square free, and we define the set M of d equals a plus b square root of d, where a and b are integers. We define the norm of x by the function n of x equals a squared minus db squared, which is an integer. And we will prove that x has an inverse if and only if n of x is either minus 1 or 1.
let x be an element of MD. X is equal to a plus b times the square root of d, where a and b are integers. We define the conjugate of x by a minus b times the square root of d. We may easily verify that the norm of x is equal to x times the conjugate of x. Moreover, it is trivial to prove that the conjugate of xy is equal to the conjugate of x times the conjugate of y, and the norm of the conjugate of x is equal to the norm of x. The norm function is multiplicative, since for every x and y belonging to MD, we have that the norm of xy is equal to the norm of x times the norm of y. Suppose that x has an inverse in MD, hence there must exist a y in MD such that xy is equal to 1. We may write 1 is equal to the norm of 1 is equal to the norm of xy, which is equal to the norm of x times the norm of y. We conclude that the norm of x has an inverse in MD. Also, the norm of x is either 1 or minus 1. Conversely, if the norm of x is plus minus 1, then the conjugate of x times the conjugate of y is plus minus 1. Hence, plus minus the conjugate of x is the inverse of x. Next slide, please. In the special case d equals minus 1, the solution is trivial. The square root of d is now equal to I, which is the imaginary unit of a complex number. Let t be equal to 1 over a plus b times the square root of d, where a and b are integers. Because t is a part of M, there must exist some integers x and y such that t is equal to x plus y times the square root of d. We get the following equation, which leads to the product being 1. We notice that both terms in the left side of the equation are complex numbers, which gives us a hint towards a good way to approach it. By applying the modulus operation to both sides and using the multiplicative property of the modulus, we get the following equation. Now we know that the modulus of a plus b times I squared is equal to a squared plus b squared, where a and b are the real and imaginary coefficients. By squaring both sides, we reach very easy to solve form, which is a squared plus b squared times y squared plus x squared plus y squared equals to 1, where a, b, x, and y are all integers. Because the square of an integer is a natural number, the equation is equivalent to n times m equals to 1, where n and m are natural numbers, and replace the first and second parentheses. Clearly, the only solution is n equals m equals 1. Therefore, the value of a squared plus b squared can only be 1, from which you get our solutions for a and b, which you can see on the screen. We reach the conclusions that the only possible solutions in the -1 case are either I, minus I, 1, or minus 1.
Now, regarding the Pell equation, a series of brilliant ideas of ancient Indian mathematicians like Brahmaputra, Bhaskara II, and Narayana related to the equation of the type a squared minus db squared as plus minus 1 were completely unknown to the European mathematicians in the 17th century. The European interest began in 1657, when Fermat issued a challenge to the mathematicians of Europe and England, looking for a solution of the equation y squared minus 61x squared equals 1. Now, several mathematicians participated in Fermat's challenge, in particular, Frenicle de Bessy, Brouncker, and Wallis. Brouncker discovered a method of solution which is essentially the same as the method of continued fractions, which was later developed rigorously by Lagrange. It is Euler who introduced the name Pell's equation, and it is generally believed that he gave it that name because he confused Brouncker and Pell, thinking that the major contributions which Wallis had reported on as due to Brouncker were in fact the work of Pell. Now, the ancient Greeks were among the first to study the equation a squared minus 2b squared as minus 1, motivated by the evaluation of the diagonal of a unit square, which equals the irrational number square root of 2. As such, they gathered arbitrarily close approximations of this particular number by using arbitrarily large solutions of the equation above. Since we may write, of course, the equation below, which has a limit of 2. Hence, if y of I denotes the side of a square, x of y automatically represents its diagonal. Defining the side and diagonal numbers as s of I and d of y by those relations, when we choose the pair 3 and 2, we get the equation d of 1 squared minus 2s of 1 squared equals 1. Now, for the general case of that particular Pell equation, you can look at the relations below. We conclude that odd index numbers d of I and s of y represent the solutions of the equation a squared minus 2b squared equals 1, while even index pairs verify the closely related equation a of squared minus 2b squared equals minus 1. Now, let us search integer numbers a and b, such as a squared minus 2b squared equals plus minus 1. When 1 appears in the right-hand side, we of course obtain a positive Pell equation, while for minus 1, we get the negative version of that. A Pell equation is a Diophantine equation, which means that it is generally resolved through different recursive steps, not all of the sudden. Now, as an important remark, since every A and B pair of solution of the Pell equation yields additional solutions of the form A minus B minus AB or minus A minus B, it will suffice to search for natural values of the A and B perimeters. Regarding the number y of 1, which equals 3 plus 2 square root of 2, that is called the fundamental solution of the positive Pell equation, which is the non-trivial solution having the smallest value. In simpler terms, the trivial solution of the equation is obtained for a equals 1 and b equals 0. Much similar to that, the number 1 plus square root of 2 represents the fundamental solution of the negative Pell equation. To start with, we remark that y of 1 equals 3 plus 2 square root of 2, which is a part of m of 2, which has the norm equal to 1, and according to the proof above, it is a solution to the associated Pell equation. Then the following number, 17 plus 12 square root of 2, also has the norm of 1, because the norm of y of 2 equals the norm of y of 1 and y of 1, which is 1. Along the same line of thought, any power of the form y of n, which is y of 1 at the power of n, has also the norm 1, and will also represent a solution of the corresponding Pell equation. Moreover, we may prove by induction that such powers are distinct. More specifically, y of 1 at the power of n could be written as u plus v square root of 2, with u and v being natural numbers. Then, of course, y of 1 at the power of n plus 1 would be 3u plus 4v plus 2u 3v square root of 2. And since 3u plus 4v is greater than u and 2u plus 3v is greater than v, we automatically conclude that y of 1 at the power of n and y of 1 at the power of n plus 1 are, of course, distinct. Hence, the Pell equation for d equals 2 has an infinite number of solutions. Regarding the general solution of the positive Pell equation, which of course is a squared minus 2b squared equals 1, that is simply obtained from the relation below, where the pair an and bn satisfy the recursive relation below, and a0 and b0 is the pair of 3 and 2, in that particular fundamental solution, which has the system written below. The general solution of the negative Pell equation, a of squared minus 2b squared equals minus 1, is indicated by the recursive relations written below, with a0 and b0 being the pair 1 and 1, which represents its fundamental solution, while xn and yn is the general solution of the associated positive Pell equation. Of course, here we can witness the graphical representation of our Pell equation, where in this particular case n equals 2. And another graphical representation for the case of n equals minus 2, which isn't necessarily quite so related to the previous discussed equations, but anyway, it is a pretty interesting graph given that it is an ellipse.
Now we'll talk about the generalization of the Pell equation. So we can take into consideration two cases. First, the positive Pell equation, u squared minus d times v squared equal to 1. We denote, in this case, knowing that d is not a perfect square, we can find an infinite number of solutions. We denote u0 and v0 the fundamental solution, meaning the smallest solutions different from 1 and 0. Now find the sequence shown here, meaning u1 equals to u0 and v1 equals to v0, and the other two relations below referring to un plus 1 and vn plus 1. Solving this sequence, we find the solutions written here for un and vn, which obviously depend on u0 and v0. And now you can see the label for the solutions u0 and v0 for certain values of d, here being smaller than 103. It's pretty obvious that if we know the solution u0 and v0, we can find all the other solutions.
And now for the negative Pell equation, we denote by A and B the fundamental solution for the negative equation, and thus before u0 and v0 the fundamental solution for the positive equation. We have a similar recurrence as before. It's shown above. Xn is aun plus d byn, and un. We have the recurrence above, and by solving the recurrence, we find the solutions. These are a bit more complicated than for the positive Pell equation, but they can still be found. Here we have to observe something. There are not solutions for every value of d. For example, for d equal to 3, we don't have solutions for the Pell equation. And now here is a table for the fundamental solutions for d smaller than 103. And the ones that are omitted don't have.
Now, some conclusions to our previous work. Of course, the Pell equation is related to square triangular numbers, which are perfect squares that also represent Gaussian sums, as shown below. In this particular example, x equals 2m plus 1 and y equals 2m. Now, of course, we may find some relations between solutions of Pell's equations and continuous fraction representations of quadratic irrational numbers, which is some complex mathematical work. And we may dive into some further study of the generalized Pell equation of the form a squared minus 2b squared equals k, where k itself is an integer.
We'll finish our presentations with a quote, which is obviously related to mathematics. So mathematics is the queen of the sciences, and the number theory is the queen of mathematics. Carl Friedrich Gauss. Thank you.
Thank you very much for paying attention.
Thank you very much to the students of Yash. Your presentation was great. Now we'll give the public a minute in case they have any questions for them to write them in the chat. Merci beaucoup, votre présentation était super. On va maintenant laisser 1 minute au public pour qu'il puisse mettre des questions dans le chat. Well, we have no questions for today, so thank you very much and goodbye. Merci beaucoup, on n'a pas de questions pour aujourd'hui, donc au revoir. So thank you very much to all the participants today. All your presentations were great. That's it for today, and tomorrow we will continue the MATH.en.JEANS Congress starting at 9:30 with Genevieve Robin from the University of Ivry. She will be talking about mathematicians, biodiversity, and citizens. Thank you, and we hope to see you all tomorrow. Voilà, et merci à tout le monde pour votre participation aujourd'hui. Nous reprenons le congrès demain matin à 9h30 avec Geneviève Robin de l'Université d'Evry qui nous parlera des citoyens mathématiciens et de la biodiversité. Merci encore et on espère vous voir tous demain. Au revoir, merci.